So this is chapter 14, which is chemical equilibrium. So first we're going to talk about, there's an application section at the beginning of this chapter that has to do with hemoglobin. And hemoglobin is a protein found in red blood cells that reacts with oxygen and actually allows your blood to carry oxygen. This is also what makes the oxygen, your blood look red, is the hemoglobin carrying the oxygen. HB represents a protein. It is not a chemical formula. The protein formula is actually very complicated. But what I want you to notice is the double arrow. Double arrow is always an indication that something is at dynamic equilibrium. Not every chemical reaction goes to dynamic equilibrium, so that double arrow is actually very specific to this certain type of reaction. Basically, the way hemoglobin works is you have red blood cells that contain thousands of hemoglobin molecules, and the oxygen, when it goes through the lungs, actually binds to the hemoglobin. So if we talk about hemoglobin in terms of equilibrium system, we're going to talk about the hemoglobin binding with the O2 to make oxygenated hemoglobin or red blood cells. The concentrations of each thing are all interdependent, and they're all related to the equilibrium constant. The larger the value of K, which is the equilibrium constant, the more product is formed at equilibrium. Changing the concentration of any one of these actually changes the concentration of the other. When a system is at equilibrium, all the components, the reactants, and the products are in direct correlation with each other. So what you can see here is in the lungs, there's a high concentration of O2. So in the lungs, you have a lot of oxygen in there, which is going to shift the reaction towards the right, towards the product, which means more of the product, HbO2, is made. In cells with low concentration of O2, the equilibrium shifts to break down the hemoglobin carrying oxygen so that you can use the oxygen basically to fuel the cells, and which is the way O2 transport works. There's also a component when you have fetal hemoglobin, which a fetal is like a fetus, like a baby before it is born. Fetal hemoglobin's equilibrium constant is larger than adults because fetal hemoglobin is more efficient at binding oxygen. O2 is transferred to the fetal hemoglobin from the mother's hemoglobin in the placenta. Remember that a baby and a fetus, the only way it's getting oxygen is through the mother, through the blood of the mother. This is why you're not supposed to smoke when you're pregnant, because anything the mother inhales, the baby's going to inhale. So basically, you're going to have the difference in concentration of the oxygen, which is going to shift the reaction towards making oxygenated hemoglobin. And this is just the biological systems of the way the placenta works and the umbilical cord and the way the fetus is getting all the oxygen and nutrients from the mother. So basically, when a reaction starts, the reactants are being consumed to make the products. The reactant bonds are breaking and the product bonds are forming. In a forward reaction, you're going from reactants to products. Therefore, the reactant concentration decreases, the product concentration increases. As the reactant concentration decreases, the forward rate is actually going to decrease. Eventually, the products react in some equations to go in reverse. You're going to get a reverse reaction. Remember, not all reactions are reversible, which will only make certain things very unique to be able to achieve equilibrium. And what happens when the reaction reverses is the exact opposite happens. The product concentration is going up, the reverse reaction rate is going up. A process that can be both forward and reverse is called reversible, and in order for you to have an equilibrium reaction, you have to have a reversible reaction. So if we look at just a hypothetical reaction, we have, red and blue, not real things. The reaction is going to slow over time, but the concentration of red, the reactant never runs out, which is a characteristic of something that's reversible. You're never going to completely consume the reactants. At some time between 100 and 110 seconds, the concentrations of both red and blue molecules no longer change. This is when equilibrium has been established. Pay attention that equilibrium does not mean the concentrations are equal. Red and blue never at any point have the exact equal concentrations. Equilibrium is when the concentrations stop changing. Once equilibrium is established, the rate of red molecules turning into blue is the same as blue turning into red. Not the exact concentrations of each, just the rate at which that's happening. So if we look at this same thing using a concentration versus time graph, you're going to see at the beginning, you're going to have the reactant concentration exponentially decreasing, the product exponentially increasing, and then around a certain time you're actually going to have the concentration staying the same, which means equilibrium has been established. If we look at it in terms of rate, so these are two separate graphs. This is showing you concentration, and this is showing you rate. Notice in the concentration graph, they never really meet, they just go horizontal. But in a rate, you're actually going to start with initially only the forward taking place. So it's only going in the forward reaction, there are no products. At the beginning, the product concentration most of the time is 0. As the forward reaction proceeds, it makes products and uses reactants. Because the reactant concentration decreases, the forward reaction slows, and as the product accumulates, the reverse reaction speeds up. So the rates are actually meeting each other. Eventually, the reaction proceeds in the reverse direction as fast as it proceeds in the forward, and you're going to have equilibrium established. Remember that this is the rate comparison, not the actual concentrations. Once equilibrium is established, the forward and reverse reactions proceed at the same rate, so the concentration of all materials stays constant, stays the same. As the forward reaction slows, the reverse accelerates and vice versa. Dynamic equilibrium is a condition where the rates in the forward and reverse reactions are equal. We use dynamic because it's moving. So if we think back to osmosis, the actual reaction never stops. It's the total change in concentration remains the same. Once the reaction reaches equilibrium, the concentrations remain constant because everything's happening at the same rate. So if we look at another example, at time 0, there are only reactants. We don't have any products made, so there are only reactants. So basically, the product concentration 0, the reaction is only moving forward. At time 16, which is just an arbitrary time in the reaction, you have both reactants and products, so the forward and reverse reactions are taking place. At time 32, there are now more products, so actually the forward reaction rate is slowing, the reverse is speeding up. And at time 48, the amounts of products and reactants have not changed, so equilibrium has been established at this time. This is the same thing, just showing you graphical form. You're seeing the reactant concentration decreasing, the product increasing, and eventually you're going to reach equilibrium. So since the reactant concentrations are decreasing, the forward rate slows. Since the product concentration is increasing, the reverse rate speeds up. At the time when equilibrium has been established, the concentrations no longer change. The rate forward is the same as the rate reverse. Since the concentration of product at equilibrium is higher than that of each of the reactants, we say the position of equilibrium favors the product. It's more likely to make product, which is you're going to see most of these. Most of these equations, it's more likely to make product than it is to make reactants. The rates of the forward and reverse reactions are equal at equilibrium, but that does not mean the concentrations are equal. That's a key factor here. Some reactions reach equilibrium only after almost all reactants have been consumed. This is a product-favored reaction. Others reach equilibrium when only a small percentage have been used. That's a reactant-favored reaction. So we look at an analogy here in terms of population change. So when country A citizens feel overcrowded, some will start to emigrate to country B. You see them moving. As time passes, emigration occurs at both directions at the same rate, leading to the populations of country A and B that are constant, though not necessarily equal. That's key. The equilibrium constant is related to the law of mass action, which says that there's a relationship between the chemical equation and the concentrations of the products. So if we look at it's just an example equation here. Notice the double arrow to indicate equilibrium. This is how you would write the equilibrium constant. So it's going to be K, concentration of each product multiplied, over concentration of each reactant multiplied, and then the exponent comes from the coefficient. For example, you can see example here of just writing an equilibrium expression from a equation. When you look at KEQ compared to 1, it tells you whether it's product or reactant favored. If K is greater than 1, it is product favored. If K is less than 1, it is reactant favored. The larger the equilibrium constant, the more it's going to be favored for one direction or the other. The smaller is when you're going to have more reactants. Again, so if K is less than 1, the reverse is favored. If K is greater than 1, the forward is favored. It's about equal to 1, neither is favored, or the reaction proceeds about halfway. You can also take the K and manipulated, kind of like Hess's law with how the equation's manipulated. So for example, when the reaction is written backwards, K is going to have a very particular change happen to it. So if we see the reaction here and the expression is written, if you reverse the reaction, if you flip it and you rewrite K backward, what you're going to see is that K backward is actually equal to the inverse, 1 over K forward. So if you were just given the K value, you could actually just take 1 over that number to find the backward value. Another thing you can look at is the coefficients. So we see in this example, the equation, everything in the equation here is multiplied by 2. When you do that, you can think of it as taking these C's here, this C and multiplying by 2, A times 2, which what you can think of as the whole thing is squared. So the way you can look at that is K new is equal to K original times whatever factor you're multiplying the coefficient by. The other thing is when you add equations to get a new equation, what you're going to do is, if you look here, you have these two reactions. You can see B is going to be an intermediate. So if you're writing K expressions for both, this is the K expression for the first, this is the K expression for the second. If you combine it into an equation, you can see B is going to be eliminated because B is an intermediate. And what you actually see happen here is if you were to multiply these two K values, the B's actually cancel out, so that the new one is actually just the new K expression for the new reaction. So the K new is equal to K first times the K second. So an example problem here, compute the equilibrium constant at 25 degrees for the following reaction. So for the original reaction, you can see the change, what happens to the reaction here. Here's your original, here's the two changes. You're going to see the first thing is the reaction is reversed, so you're going to take the inverse. And then the reaction is also, the coefficients are multiplied by 1/2, so you take it to the power of a 1/2. That's actually also the square root to get the K. To do the new K, you kind of use a little hash mark here, and then finally your new K expression is 5.2 times 10 to the negative fifth. When you're dealing with gases, remember that you don't deal so much with concentrations, you deal with partial pressures. So that's just going to change a little bit how you write the K expression. First, you're going to use something called Kp. So if you're given this equation here, you would normally write it concentration with the brackets. But if you're using all gases, you're going to actually use P for partial pressure. And then the subscript is going to be whatever gas you're talking about. But you're still taking it to the exponent, which is equal to the coefficient, and still multiplying. Everything else is the same. You can relate Kp and Kc with this equation right here. So Kp is equal to Kc times RT to the delta N. R is the gas constant, it's 0.0821. T is the temperature in Kelvin. And delta N is the difference in the number of moles of the products and reactants. You're going to use that just looking at the equation. This slide here just tells you how you derive that relationship. As with this one, I'm not really concerned that you understand where it comes from, just that it's related to the concentration and the pressure. Really, the big thing is that you know the equation down here. So find the Kc for the following reaction given the Kp. So first thing I'm going to do is find the delta N because that's part of the equation here. So I'm going to have 2, which is the total number of moles of product, minus 3, which is the total number of moles of reactants, to get negative 1. The 2.2 times 10 to the 12th comes right from the problem here. 0.0821 is the gas constant, and 298 comes from the Kelvin temperature. Take it to the negative 1, which is the delta N, and you get 5.4 times 10 to the 13th. When pure solids and pure liquids come into play, it changes a little bit the equilibrium constant. The pure solids and pure liquids are materials whose concentrations don't change. Therefore, they are not involved in the equilibrium. So when you're writing the equilibrium expression, you do not include any solid or liquid. Anything that has an S or an L is not included in the equilibrium expression. Basically, the only thing you're going to include is a G for a gas or an AQ for an aqueous solution. And this slide here just depicts that the amount of C has no effect on the equilibrium position, so the solid carbon is not going to be included. The most direct way of finding an equilibrium constant is to measure the amount of reactants and products and calculate it. The equilibrium mixture may have different amounts of reactants and products, but the value of the equilibrium constant will always be the same. It's kind of like a ratio. The only thing that's going to change the equilibrium constant is going to be the temperature. That's the only thing that's going to change the value of K. So if we look here, you're just given a series of equilibrium concentrations, and really you're just plugging them into the K equation to get the equilibrium constant. If you look here, changing the equilibrium concentration. So here they're all different equilibrium concentrations, but you notice the ratio, the K, the equilibrium constant, is always the same number. It's always 50. The only thing that changes the K, the equilibrium constant, is the temperature. So there's going to be a couple different ways that you're going to be able to calculate K, that you're going to be calculating equilibrium concentrations. One of the ways is using something called an ice chart. And an ice chart is where you're going to have initial molarity, change in concentration, and equilibrium molarity. That's where the ice comes from. So a couple of sample problems. It says find the value of Kc for the reaction if the initial concentrations are given and the equilibrium concentration of C2H2 is given. So the first thing you're going to do is construct an ice chart. You don't have to write at the initial change equilibrium. You can just write ICE. You're going to write your reactants and products. I like to write this more as an equation with the actual arrows and plus signs so you know what's what. I fill in my values given. 0.115 is given right here in the problem. When you're not given the value of reactants or products, you just assume that those are zeros. So that's where those zeros come from. I am then given the equilibrium, the E concentration of C2H2, which is what I put here. And what you're going to be able to figure out is the change that occurred is 0.035. So I know that I added 0.035 there. So what I can figure out is the equilibrium concentration of each thing is going to be changing by the same amount. So I'm going to subtract 0.035. Now notice I multiply it by 2, the coefficient, and then I'm going to add 0.035 multiplied by the coefficient to the other side. Notice, almost always, you're going to assume the reaction is going in the forward direction. So you're going to subtract the concentration of products, and you're going to add the concentration of reactants. And the coefficients do come into play. You have to remember to multiply by coefficients. So when I do the math, I'm going to get 0.05 for CH4 and 0.105 for H2. I simply plug that into my KEQ expression, and then I solve for K, which is 0.02. The same thing here, you're going to see the following data. You're going to calculate the Kc. This one actually gives you the equilibrium concentrations here, so you don't have to do the minus and the plus. You can see it here. It's the same as a nice chart, but then I'm going to plug that in to Kc and Kp and solve to get 4.7. The reaction quotient Q is basically the same expression. You're writing it the same, products over reactants. The difference is the reaction quotient is calculated when substances are not at equilibrium. Calculating Q helps you predict how close a reaction is to reaching equilibrium and whether it's proceeding in the forward and reverse direction. So the reaction quotient is written the exact same as the equilibrium constant, whether you're going to use concentration or gas pressure. But you notice you're going to solve for Q, not K, because Q is for not at equilibrium concentrations. When you compare Q and K, that gives you an idea of where the reaction is, where it's proceeding. So if Q is greater than K, the reaction is actually moving fastest in the reverse. The products are going to go down, the reactants are going to go up. If Q is less than K, the reaction is proceeding forward. The products are going up, the reactants are going down. That's going to be the most common. If Q is equal to K, the reaction has actually reached equilibrium. If Q is 0, basically that means you're at the very start of the reaction, so it's moving forward. And the thing that you're very least likely to see is if Q is infinity, that means it's going to go in the reverse. So if we look here, this just tells you the different values of K and Q and how you're going to see them proceed through the reaction. So this sample problem says for the reaction below, which direction will it proceed? And it gives you some partial pressures. Notice it doesn't say partial pressure at equilibrium. So when it's giving you concentrations or pressures not at equilibrium, you use Q. Remember, Q is written the same way as K, the expressions. You're plugging it in the same way, and you're solving for Q, which is 10.8. Now in this case, it gives you a Kp, so you can see that the Q was less than the K, which means the reaction is proceeding right or proceeding towards the products. So this one says a sample of PCl5 is placed in a 0.5 liter container and heated. The PCl5 is decomposed into PCl3 and Cl2. At equilibrium, 0.203 moles of PCl3 and Cl2 are formed. Determine the equilibrium concentration. So here, I'm given actual equilibrium concentrations. Now notice, concentration is always moles per liter or molarity. So I'm taking my moles and liters and dividing it to get molarity. The key here is you're solving for an actual concentration. So you're actually given the Kc, you're solving for a piece here. Same equation, same plug-ins, you're just solving for a slightly different number. In this case, you're going to get PCl5 to be 2.6 molar. You're also going to be able to figure out how to solve for equilibrium concentrations and eventually K and Q when you don't have the change. So what you're going to do is you're going to define the material in terms of X, and you're going to add or subtract X, remembering the coefficient, keeping that in mind. And then you're going to solve for S to get the concentrations, and then you're going to solve for K. So here's an example problem giving you an equation. It says for the reaction, if the initial partial pressures are all 0.1, find the equilibrium concentrations. So here, the only thing I'm given is initial concentrations, which I've written here. I don't know what the change is. So just like in math, when you don't know what the change is, what you're going to use is X. Now this has you find Q to tell that the reaction is proceeding forward. And technically you should always do that because sometimes the reaction could be going in reverse, which would change your positive and negative signs. You can also pretty much assume most reactions are going forward, but the only way to tell for sure is to solve for Q. So what I'm going to do is I'm going to say, okay, I know my changes are going to be in terms of X. I know that my products are always added if it's going forward. My reactants are subtracted. That's where the Q comes into play, because if it was going in the reverse direction, you would have plus X, and then minus 2X. Remember, the 2 comes from the coefficient. And then what I'm going to do is I'm going to give the equilibrium values in terms of those X's. Then I'm going to plug that in. I'm given Kp, and this is where you're going to have your, your FOIL and first, outer, inner, last, and figuring all those kind of things out. And you're going to solve for X, and you're going to get X to be 0.0729. I'm going to show you a shortcut in a second, but this is the long version of foiling it and solving for X, etc., and so forth. Once I have my X value, though, I am not done, because the X value is just telling me the change. So what I have to do is take the X and substitute it, and then actually solve for my equilibrium concentrations, which I'm doing here. You don't have to put them back in the ice chart. You can just kind of circle them on your paper, but that's kind of, you got to make sure that you're fulfilling the problem. The problem may not be asking you for X, it may be asking you for concentrations. And then here you're going to check your work by using those numbers to solve for Kp, and you see that your answer is correct. A next problem, for the following reaction, the value of Kc is at 1,000 degrees. If 1 mole of I2 is placed in a 2-liter flask and then heated, what will be the equilibrium concentrations? Notice I've made my ice chart. We know it's proceeding forward. I'm given 0.5. Remember, if you're not given another initial, you just assume it's 0. I do my changes in terms of X, and then I'm going to solve. Now here, in order to solve this, because of where the X is, you actually have to use the quadratic equation. So you're going to get X to have a value of 0.002. And then from here, you plug that in to get your equilibrium concentrations and so forth. Now, obviously, using that quadratic is probably not everyone's favorite. It's not something you want to do. So now we're going to talk about a shortcut. We're going to use an approximation. And what we're going to say is when the equilibrium constant is very small, meaning if the equilibrium constant has a value of a number times 10 to the negative third or greater. So if it's times 10 to the negative third, times 10 to the negative fourth, times 10, we're going to say that that number, the change in X, is so small that it's insignificant to our mathematical operations. Whether we have the X in there or we don't, it's not going to really pay attention to our math. What you should do is make an approximation. You should take the approximate X over the initial concentration to figure out whether it's less than 5%. Again, as a time saver, you can pretty much assume that you're going to be able to approximate. It's easier, I think, to assume the approximation than to do the quadratic. So for example here, for the reaction, you're given a Kc, and notice the Kc value is times 10 to the negative 7th. That is way higher than times 10 to the negative 3. So what I'm going to be able to do is assume X is very small, and I do that by looking at the Kc here. If you have a 0.5 liter flask initially containing 1.25 times 10 to the negative 4th moles, and then you heat it, find the equilibrium concentration. Notice everything starts with my ice chart. I'm given 2.5 times 10 to the negative fourth in the problem. I'm not given any product number, so I'm just going to assume they're both 0. We're going to say Q is going to tell us it's going forward. So I'm going to use X to define the change. Remember, you subtract, if it's going forward, you subtract products, add reactants, and then going to rewrite. Now here's where the easy part comes in. For this part here, where you're taking a number and you're subtracting by X, and we're assuming X is very small, what you can do is say that this change here is going to be insignificant to my final math. So you can actually just get rid of it. You need to say that it's very small. You have to cross it out and kind of point an arrow and say it's very small. But when you get rid of that, the math becomes very much easier. Basically here you just take a cube and you solve, and you're getting x times 10 times 1.38 times 10 to the negative fifth. That's much easier than doing the quadratic. And then again, remember, this is going to take the approximation, which is going to tell you you're fine. If it's not valid, like in this case, you're supposed to go back and do it with the formal numbers, you know, taking it, not taking the x. But again, your answer is actually going to be very close to what the answer should be. So I'm going to get x to be 1.28 times 10 to the fifth, negative fifth, plug that in for all my x values to solve for the equilibrium concentrations. And then again, you can check your answer by plugging that back into the K expression to get the correct number. Again, we're going to use the simplifying for x here. It's going to go forward. I'm going to take minus x plus 2x here. I'm going to pretend that this x right here is very small, and changing the 0.5 by this number is not going to be significant. So when I get rid of that x, it makes it much easier to solve. So I get x to be a value of 2.17 times 10 to the negative third, and if I check that, the approximation is valid. Take that x value, plug in to get my new concentrations, check by plugging into the Kc, and we're good. Next thing we're talking about is, okay, you have a reaction that's at equilibrium, then you make a change. What's going to happen to the reaction? The reaction is going to shift. It's either going to shift to the left or to the right. The new concentrations are going to be different, but the equilibrium constant will be the same. This is known as Le Chatelier's principle. These principles guide us into telling which way the reaction is going to shift. So there's a couple, here's the analogy first. So we have the countries that we were talking about before, population A and population B. They are at equilibrium at this point. And then all of a sudden we get a disturbance in equilibrium because we're going to get an influx from a population from outside these two countries. So what's going to happen is you now have a lot of people in country B. It has disturbed the equilibrium. So what's going to happen is the people are going to start shifting again until equilibrium is reestablished. There's a couple of guiding principles here. First, if you're going to change the concentration, whenever you add, if you add a reactant or you add a product, the reaction shifts away from the addition. If you remove a reactant or remove a product, it's going to shift towards the removal. So here's just telling you adding the reactant has no initial effect. It actually is going to go right until equilibrium is reestablished and the value of the equilibrium constant stays the same. Again, if you remove, it's going to shift left. The equilibrium constant stays the same. This is what's going to look like graphically. So actually right here you see the shift. You can see a dramatic increase at a specific time. Notice the equilibrium constant is going to be the same number. The concentrations won't be the same, but the equilibrium constant will be the same number. When you have a gas, adding a gaseous reactant increases the partial pressure, causing the equilibrium to shift right. Adding an inert gas has no effect. So if you're adding a gas changing the pressure for gases, it's always going to move to the less occupied area. So if you increase the pressure, the gases or the reaction is going to shift to the side with less moles. Again, same thing, you're going to see a great disturbance, equilibrium getting reestablished. Volume and pressure, you can kind of think of the same. If you're going to decrease the volume, you're going to increase the pressure, which again is going to be the same kind of shift. It's going to shift to the side with less moles of gas. Same with reducing the volume, it's going to go opposite. It's always going to, when you think of volume, kind of think of the way it's going to affect the pressure, and that's going to tell you which way it's going to shift. This is just showing you since there are more gas molecules on the reactant side, the pressure is increased, so the position shifts towards the products. When the pressure is decreased, it's going to actually shift the other way towards the Mohr side. Now, temperature is very key with Le Chatelier because temperature is the only thing that's going to change the equilibrium constant. The equilibrium constant K will change with a change in temperature. One thing you're going to have to really know is whether your reaction is exothermic or endothermic. When it's exothermic, you write heat as a product. When it's endo, you write it as a reactant. And really, you can just look at it in terms of, are you adding a product or are you adding a reactant? It's going to shift away from the heat. This is just showing you that in picture form, but remember, the key to a temperature change is not so much the shift, but that it's going to affect the equilibrium constant. We talked about catalysts last chapter. Catalysts speed up a reaction rate by reducing the activation energy. Therefore, catalysts do not affect the position of equilibrium. This is just a practice you can do with yourself, telling you which way things are going to shift by adding reactants, changing volume, etc., and so forth. And that concludes the Chapter 14 lecture.